Electric potential energy. Now today's topic is electric potential energy. Suppose here is a charge plus Q, that is a source charge, and this charge produces an electric field E. Now in this electric field I am considering 2 points, point A and point B. Suppose a charge Q naught or Q. Suppose a charge Q is placed at A. So this charge experiences a force. So it is a positive charge. So experience a force F in the direction of electric field. So to move this charge from A to B, some external force is required. So external force, this F is equal to QE, because as we know a charge Q in electric field experiences a force QE. So what is F external? F external is equal to minus of F. Suppose this charge which is initially at A, now it is moved to A dash by a small distance dx or small distance dr, whatever you can say. Suppose if I take this dx as dr, this charge Q is moved from A to A dash by a small distance dr against this electric field. So the work done by the external force dW is equal to F vector external dot dr vector by the definition of work done. So the total work done in moving the charge Q from point A to point B, that is W. So W is equal to integration from A to B F external dot dr. So this is the work done, and this work done is against the electrostatic repulsive force. This work done is against electrostatic repulsive force. So this work done gets stored. As potential energy. So the important thing, at every point in electric field, a particle with charge Q possesses a certain electrostatic potential energy. Every point in electric field possesses some electrostatic potential energy. So this work done that I have calculated here, this work done increases its potential energy by an amount equal to the potential energy difference between point A and B. So this work done increases its potential energy by an amount equal to potential energy difference between point A and B. So this W is equal to delta U. So this W is equal to delta U, potential energy difference, that is UB minus UA, because the charge particle is taken from A to B. So final potential energy minus initial potential energy, and this is equal to WAB. So this work done that is stored in the form of potential energy is equal to the change in potential energy, not only the energy at a point. So this is the important thing about potential energy. And also the work done, as it is clear from this equation, the work done in moving a charged particle from point A to point B depends only on initial and final position. So the force by which the work is being done is a conservative force. यहाँ पर ये जो force है, this force is a conservative force. Because this work done is path independent. This work is path independent. So conservative forces are those forces by which the work done does not depend upon the path. It depends only on initial and final position, which is clear from here. Now so here is a formula for change in potential energy. Now there is a freedom. There is a freedom in choosing the point where the potential energy is zero. So a convenient choice is to have electrostatic potential energy zero at infinity. So we can consider a point where potential energy is zero, so that point is infinity. So I take the point A is at infinity. So if A is taken to infinity, so the potential energy at this point UA will be 0, that is at infinity. So from the above relation we have UB minus U infinity is equal to W infinity B. So U infinity is 0. So we have only UB minus 0 is equal to W infinity B. So we get only the potential energy at point B. From this expression we have potential energy at point B. This is equal to W infinity B. So the above equation provides us the definition of potential energy of a charge q at any point. So this expression, the above expression, gives the potential energy at any point. So potential energy of a charge q at a point, and that point is in electric field, is the work done by the external force equal and opposite to the electric force in bringing the charge q from infinity to that point. So this is the definition of the potential energy at a point. Now we come to the next point, potential energy of a dipole in an external field. If a dipole is placed in external field, what will happen? So here is a case. Here are two charges. One is plus q, one charge is plus q. So on this charge there will be a force in this direction. F1 is equal to QE, while there is another charge minus q. So the force on this charge will be F2. So F2 is equal to minus Q of E. So here is a dipole moment vector P. So here is an electric dipole having minus q and plus q charges separated by a short distance 2a, and the dipole moment vector points from minus q to plus q, and it is at an orientation theta with the electric field E. So whenever any dipole is placed in electric field, it tends to align itself either in the direction of E or opposite to direction of E, means parallel to E or anti-parallel to E. So the torque on the dipole, as we have discussed earlier, it is P cross E or PE sine theta. This is tau. And the magnitude and is a unit vector perpendicular to the plane of paper. So here the direction is invert the plane of paper. So if I want to rotate this dipole, suppose this dipole is rotated by an angle d theta, so tau external is applied. Suppose it is rotated by an angle d theta. So the work done dw is equal to tau d theta. So tau is Pe sine theta d theta. This is dw. So here this torque is external torque. This torque is external torque. So dw is equal to Pe sine theta d theta. Now the dipole is rotated from angle theta 1 to theta 2. Now the dipole is rotated through angle theta 1 to theta 2. So total work done W will be integration from theta 1 to theta 2 Pe sine theta d theta. So Pe comes out, integration sign, and the integration of sine theta is minus cos theta. It is theta 1 and theta 2. So by putting the limits, Pe minus cos theta 2 minus cos theta 1. So this W becomes Pe within bracket cos theta 1 minus cos theta 2. So this work done by the external torque. So this work done gets stored in the form of potential energy. This work done gets stored as potential energy. So as we have seen earlier, this work done is equal to change in potential energy. It is not the energy, it is the change in potential energy, delta U. So delta U is equal to Pe cos theta 1 minus cos theta 2. So here the change in potential energy means potential energy at orientation theta 2 minus potential energy at orientation theta 1 is equal to Pe cos theta 1 minus cos theta 2. So as we have seen earlier, there is a freedom to choose a point where the potential energy is supposed to be 0. So if we want to the potential energy at orientation theta, potential energy at theta orientation, so we have to take theta 1 is equal to 90 degree and theta 2 is equal to theta. So we have U theta minus, and the potential energy as u theta 1 is cos theta 1, P cos theta 1. So this will be 0. So at this theta 1, potential energy will be 0. This is important point. So u theta minus 0 is equal to Pe cos theta 1 is 90 degree minus cos theta. Cos 90 is 0. So u theta is equal to minus Pe cos theta. So this is the formula for the potential energy at an orientation theta. So these are the topics which I discussed today. अगर आपको ये टॉपिक समझ में आए हों और अच्छे लगे हों तो कृपया हमारे यूट्यूब चैनल को सब्सक्राइब करें और लाइक करें और शेयर करें. थैंक यू.